Good. So thanks Mario for the introduction. I'm happy that you have such a big opinion of me. I mean, the purpose. I was actually happy to give this talk because it's an introductory talk on SLAM and on some recurrent patterns in of research in general that we observe. So for those that are not familiar with SLAM, then it might be interesting to know how a field that it's now 30, 40 years old evolved over time. And for those that are doing research in general, it might be like a fun presentation to see how we often follow trends, get in love with some principle, then get rid of this principle, and then marry it again some years later. Just think about the neural network 20, 30 years ago and now. So let's start with a soft introduction on smart agents in general. Well, a common paradigm when we construct an agent in general, and in particular a robotic system, is to develop a machine that has to sequentiate three steps, that has to progress in three by following three actions, three tasks. First is sensing the environment. So an agent is normally required to carry on a task, and this task is described as its desired word configuration. Like to achieve this desired word configuration, the agent needs to look around and with its sensors to update an internal representation, a data structure that describes this environment to the extent of the accomplishment of a plan, to the extent of knowing enough about the environment in order to carry on the plan. So the word representation is normally at an abstraction level that is sufficient for the agents to carry on planning and it's not too complex in order to actually do the planning effectively. Then once the agent has looked around or repeatedly looked around, he has an idea on how the world looks like, and then he can carry on a plan. He can calculate the best sequence of actions that will modify this word representation that is going to be resensed as the agent moves in the environment in order to match the desired word configuration that he has in his head or that is his goal. And so to carry on, it will have to plan to determine this action. Then these actions, in particular, in case of a robot, needs to be executed, needs to be translated into motor commands that will, in the end, result in the machine to move. Like to have an idea of this architecture in place, here we have a manipulator robot that is asked this orange thing here that is asked to categorize certain metal parts that he sees in front of him and to pick up these parts based on their shape, recognizing them within a database of objects, and then picking all objects of that size of the same sort and putting them in a box. In box number one, box number two, box number three. So here you just like see the entire game of sense plan act, because each time the robot looks, he has to use his cameras, use his sensors to figure out that will return in the end either an image or a depth map of the object that he has in front. And then based on this depth map, which is not suitable for carrying on the plan, he will have to identify shapes, and presumably his word representation will be consisted in the 3D positions of the identified objects plus some obstacles. And then it's a much more compact representation because I just need to store a set of transforms and IDs for the objects, and then maybe a voxel map for the obstacles. And then based on this representation, I can try to figure out the grasp position, plan an action for an object, so plan a path that will bring the manipulator to that object, grasp that object, and put it in the appropriate box, right? In a much simpler context, another architecture, another classical platform that we operate with our mobile robots. Now, mobile robots are extremely important because basically they are everywhere. And think about the Roomba, think about the Kiva systems that are managing warehouses. Think about autonomous driving and whatsoever. I mean, now I believe that with COVID thing, also telepresence robot might kick in certain environments. So like it's an essential thing, ability of a mobile having a mobile, so a functioning mobile robot. But a mobile robot is just a tool with wheels or with legs or sometimes with blades. So if it's a UAV, that is able to accomplish that should be able to accomplish basic tasks, such come here or go to that location, or more, and that's the basic action, or more articulated actions, more articulated tasks like find my wallet, or maybe bring me to the airport, which in the end is boiled down to a simple go to location action, right? Go to location, wait for me to enter the car, and go to other location. That's gonna be. But in the end, the go to location is the action that the mobile platform has to execute. Now, in order to carry on this action, this task, the robot needs to determine a configuration of the world. And in this context, the configuration of the world is where the robot is in the world and how the world looks like. In many situations, we already know how the world looks like because maybe we have a floor plan of the building, or whatever. We know the position of certain tags. Also, in case of GPS, well, GPS provides us localization because in the end, what we do with GPS is just receiving the signal from certain objects that know where they are located, and in this signal they tell us where their location is. Then by some game of clocks we figure out our distance from these devices, and then we can triangulate their position. So like it's a localization system in the end, GPS. Now in the very common case, or in the classical case when we have the map, well, the problem of my state, my internal representation, boils down to my position in the environment because the map is given, right? So that doesn't need to be estimated. Of course, the map will be taken into account to plan a path, but the map is given. It's not a quantity that I need to estimate. Eventually, I might figure out whether there is some obstacle on the way, but the map is given, right? So in this case, if I want to build a simple robot that goes from A to B, the first task that I will have to do is to figure out, to define a state for this robot. In this case will be the position. And the task of localization will be to use the sensor data to determine the position of the robot in the environment as the robot moves. Like here we see a simple example of a localization system in action. This is a map of an environment, a grid map, where each dot represents an hypothesis of the robot position. And what we, at the beginning, these points are more or less uniformly distributed. And what we want is that as the robot moves, these points will converge, let's say, well, on a location, which is the location where we expect the robot to be. And which location is the best? Well, the location that has that is most consistent with all the measurements made so far. Then once we have resolved this problem, which is called localization, we can carry on the problem. We can approach the problem of planning that will take into as input the current robot position and the target location, then do run any of the A star, B star, C star, D star, whatever planning algorithm that will return us a path of feasible configuration that will bring the robot from the desired location to the goal. And then with our controllers on the robot, we will be able to presumably execute this path. the same holds also in 3D, right? Like, so what we have seen is a 2D example, but the same system, the same principle holds also in 3D. So in this video, you see a funny robot that was required to go to the upper floor. That's more or less here. Do you see the mouse? Okay, that's more or less here. And what you see on the right is what the robot thinks about the environment. What you see on the left was Rainer that was following the robot with a camera to show, like, trying to have a view which was consistent with this one. Also, in this case, the map was built a priori. And then there's a small, this is a video that I've stolen from YouTube. I think it's a DARPA challenge video. And well, that's one consideration about robots, that robots, you know, the more a robot is useful, or the more a mobile platform is useful, the more damage it can do. Like tiny little robots, okay, there is a whole branch of research on this nano robot, on this distributed tiny robots stuff, but in general, industrial, a robot that can carry on an important task is typically huge. And if it's huge, it can do a lot of damage. Like in carrying on these actions, and as roboticists, you will all confirm, that's one thing that a robot, the basic requirement that we ask for a robot, it has to work. At least it has to be reliable, right? Because if it's not, we're going to lose also economically a lot. Go on. Now, what happens if we do not have this map? Well, the sensing, the environment representation of the robot is not known a priori. And the only thing that we have at our availability to construct this representation are the sensor data. In this case, we are talking about simultaneous localization and mapping, because we want the robot to move in the environment, and while moving in the environment, we want it to construct the map of the part of the environment that it has seen. And at the same time, we want the robot to update its location in the map under construction. Now, what you see in this video is a robot equipped with a laser rangefinder, which is moving exactly in an environment. The blue thing is a path that the robot is following. And as long as the robot moves, it has to accomplish one basic task, which is basically estimate the next position given the previous one. And in order to do so, it will typically do some matching between the sensor data that he has acquired at the previous and the current step, or run a local version of localization. Then there is another aspect, there is, it's not cooperative, okay. There is another aspect that is quite relevant, which is the so-called loop closing. In doing this incremental estimate that you see here, the robot belief about its position is slowly drifting, because each time it's doing a little error, which is never going to be corrected. And then it's of fundamental importance, the action of determining when a place has been seen a second time after having been seen in the past. This task is called loop closing. And the detection of a loop closure affects potentially the entire structure of the map. Because imagine that you're moving in a new city, imagine that you're moving in Rome, you see the Colosseum the first time, then you wander around, and at a certain point you think of being in St. Peter, but you see again the Colosseum. And this observation, seeing again the Colosseum and seeing it, having seen it in the past, will actually like remodulate the entire belief about your trajectory in the past, and accordingly about the map, because you have to make this observation of the Colosseum now and before consistent with your spatial estimate of the map. And once you have the loop closure in place, then another problem that is inherent in Islam is the optimization. So figuring out a layout of the trajectory of the robot that renders all observations maximally consistent. With observations, we mean incremental motion and loop closure events. And this is what we will be talking now. SLAM. Now, SLAM is 30 years old. Actually, it's much older because a lot of what it's used now in SLAM has been reinvented from cartography. So people in cartography were doing maps long before that then we had robots. Simply they didn't have automated procedures, and they could rely on very smart heuristics in determining places, which were based on humans that were looking at photos. But a lot nowadays steals from, or a lot in the late 2000s as stolen from photogrammetry first and then computer vision. Now, by the day beginning, the SLAM was for roboticists, and roboticists focused on having a system that was providing a real-time estimate about the map. And what roboticists do when a task is hard, they simplify the task by adding a structure to the environment. So like it was a common idea in the 90s that the world was made of landmarks. Landmarks which are like looking like these discs, which were nicely painted in a building, and the robot equipped with a camera and a very simple algorithm for detecting these circles in the image was revealing basically the presence or not of a landmark. So the map was nothing else than a set of points where each point corresponds to a landmark. Okay, having such a simplification of the map resulted in the possibility of running algorithms like Kalman filters, or in general filters, for tracking the joint state over the robot position and the landmark observations, where the landmarks were nothing else than stationary components of the state that were projected between one frame to the next without changing basically. So the transfer function was an identity. And with this system, that was more or less what the robot was processing inside. So what you see here is the trajectory of the robot. In red, the green crosses are the landmarks together with all observations. And then you might see that the loop closing effect is also evident in this system. At a certain point, it will close a loop. Yes. When it closes a loop, you see that the entire map readjusts. And this was done basically implicitly with Kalman filters through the update of the filter itself. Then something fancy happened in the community, and was that these sensors here started to come out, the laser rangefinder. Actually, they were out even before, but they were horrendously expensive. Laser rangefinder, for those that are not familiar with them, are just devices that measure distances along a scanning plane. So basically, it's a laser that is mounted on a mirror. The mirror is rotating, deflects the beam on a fan, on a plane actually, as the mirror rotates, and is able to measure distances along these beams. And then you have these nice measurements like this one that we call scans, right? Now, what do we do with scans? If I give you two scans, I mean, believe me that it's almost impossible to resist from the temptation of aligning them and to make them overlap. And so the first scan matching algorithms, which were algorithms that given two scans, they were determining the transformation of a scan with respect to the other that resulted in the maximum overlap. And here is an example of a scan matcher. You see, I guess it's pretty clear. We start from an initial configuration of scan A and scan B. Scan A is black, scan B is blue, and the algorithm basically seeks for a configuration of that results in the most likely alignment between the two. And once you have this transform, what do you do? Well, imagine that I have a data set which is consisting of a gazillion of scans, and then imagine that I have a very powerful algorithm that is able to register two scans, so to determine the relative transformation between one and the next. Well, then it comes natural to ask yourself or to formulate the problem of global optimization, where basically you ask yourself, what is the configuration of these scans, so the 2D positions in this case, that maximally satisfies the constraints induced by the registration. Then you can picture this problem as if it was a graph, where each scan is a mass, and then there is a spring which has an equilibrium point at the minimum reported by the scan matcher that describes the constraints induced by the scan matching. And we want to find and this spring is at zero energy when two scans, two poses are at a position that is the position reported by the scan matcher. But normally these positions might be conflicting because one scan might like the other, but not might like the third. And so we want to figure out the configuration of all scans that is maximally consistent with the constraints induced by these springs. Okay. And we ended up in, oops, it's not cooperative, open office, evil. Ah. No, it's not cooperative open office today. Okay, like it was very quick, but here you have seen the idea of a graph optimization algorithm. Okay, now going on, and then nothing is not cooperative. Start again. There was a shortcoming. Here we are in 92, more or less. There was a shortcoming that solving such a problem was boiled down basically in solving repeatedly was done by Gauss-Newton that involved the solution of a very large linear system. A linear system was proportional to the number of scans or to the number of measurements that we had in the map. And therefore, people that were using the classical algorithm for solving linear system, when the linear system becomes huge, well, it might take a long time to optimize it. And then this was hindering the possibility of doing it in real time or online more than in real time. So people stopped using this sort of so-called graph approaches, and they came back to filters. In that time, particle filters were very, very popular because they were solving well localization. And so people started saying, okay, if filters function for localization, why couldn't they function for SLAM? And so they started to, me also, because I was also in the pool, they started to investigate the use of particle filters in particular, which are Bayesian filters that represent the belief as a set of samples in the state space, where each of these samples was representing one potential trajectory of the robot. Now, it turns out that SLAM has a certain structure that allows to efficiently represent these samples, store these samples. And then the first particle filter for SLAM, following the work of Montemerlo in 2000, I think, was Fast SLAM, were coming out. And they were looked with favor by the community because they were addressing a lot of problems of the Kalman filter, the nonlinearities, and a lot of problems. And they were like, come on, they were in the fashion of the moment. They were working, but what was the problem is that, well, basically, in order to function, a particle filter requires to have a density of sample that is adequately representing the belief. Now, in order to have such a density of samples, you need to have a number of samples that potentially grows exponentially with the dimension of the state space. Now, with SLAM, you were lucky because the belief was very concentrated, so you could live with relatively few samples. But the dimension of this belief, being each belief consisting of the potential trajectory of the robot, was growing over time, and so the number of samples would potentially grow exponentially. Required would potentially grow exponentially. So, like, and then the people turned around, turned back. From these approaches. Okay, they were working up to a certain size of environment, but they couldn't scale more than that size. And then someone, Frank Dellart, and but before that, I think also Kurt Conolidge, were realizing something astonishing, that in this graph that we have seen a couple of slides ago, the linear system coming back from the graph uh, was very sparse. Now, well, if I have to solve a linear system, and if the system is sparse, well, I could very well use sparse solvers. It's like what mathematicians have been doing, like or mathematical engineers have been doing since ages. And so people after a long time said, oh, you know what, that thing that we couldn't do, actually we can do it because the graph is sparse. Meanwhile, also consider that the computation was the available computation was growing. So at the beginning we were constrained with very limited computation, and then we started having more powerful computer, more memory, and so we could go back to this very convenient formulation of SLAM, which is the graph-based SLAM, because it's also very pictorial. You know that a pose is a position of the robot or is a local map. You could see the constraints, you could see the connections, and then you can implement all sort of machinery on them, because in the end, it's a data structure. But once again, it happens that this once you have a nice meal, you want to have more of it. Or once you have a system that is working, you start using it, and at a certain point, the amount of data or the size of the map cannot be managed anymore in real time, even if you use a sparse solver and all these nice new back then things. So then what you see in this image is the data set, which is consisting which is obtained by a robot equipped with a camera. You don't see it, but inside this sausage here, there is the trajectory of the robot coming from the odometry, and these little dots are the 3D locations of points which have been detected by the camera. Now, to this point, we also attach a feature. We attach something that will let us recognize this point in another image. But this is actually like the input of our localization or our optimization algorithm. Now, if we try to solve this problem as it is, as a whole, then this is more or less what we get. The evolution of the incremental solver. It's trying to do its best. It takes, I think, half an hour to do this job. Then you figure out, this is not really like feasible. First of all, because I have to wait an hour. And second, because I have the impression that I can do something smarter. Well, something smarter comes from the structure of the problem. Like if I have to map a city, I don't have to care about another city. It would be much better to map local regions of the environment and then put them together with some higher level constraints, and then to determine a global configuration of these local maps, and then put them together and run once again a low level optimization only in the regions where we are interested in. And the same can be done with this problem by sparsifying it, getting higher order constraints, and then we get, actually this was the layout of the path, the trajectory that the robot has followed, and we get a more decent map in less time and also quicker. Of course, the same concept can be done online, like having a hierarchy of maps, one on top of the other, a hierarchy of graphs, where graphs at high levels represent portions of the graph at low level. And then you basically update the structure of the high level only when the low level changes substantially. And in this way, and you carry on local optimization. And this was the track basically of the hierarchical optimizers in the community. We are around 1812, 2012. Then after that, okay, you get the idea. If you have questions in this figure, You see in red the low level graph, and in blue the higher level graph, and the two are consistent. The low level graph is always augmented. The high level graph is modified only when the low level graph changes substantially. And you always have a global configuration of the environment, which is more or less where it is. And this will help a lot. The optimization algorithm that always starts from a decent initial guess. Oops. And then another thing came out the Kinect in this time, actually, the Kinect. And this resulted in people being super happy because it was cheap. It was developed for the game industry, so that it was a off-the-shelf component, and it was providing unforeseen depth measurement for that time. And people were more or less as this guy. I was one of them. And the very first thing that they did was a new algorithm, which was basically an extension of a scan matcher in 3D. In that time, there were two things that came out: the Kinect sensor and the GPU, the GPU were becoming available. And so, by putting these two trends together, we arrived at having the first, not we, the community, arrived at having the first dense registration real-time system, which is King-Fu, which I will now show you. Now, the presentation was so big that I could not include anything else. King-Fu was able to process the depth measurement of the Kinect and build a 3D representation of the environment in the form of a voxel grid in real time using a GPU. This was cool. A lot of people got depressed because when they saw it working, they say, okay, my work as a slammer is finished. Let's put it on the robot, right? Let's put, this is the number of core of the GPU cores. So yeah, you required a heavy GPU. But now, now, if you're a roboticist, you tell me what happens when you want to put a GPU with many, many cores on a mobile robot. It happens that the batteries last 10 minutes, right? So, the results were visually pleasant of King-Fu. The problem is that it was basically optimized for table scale environments, and we wanted to use it on the robots. So what we started doing was to develop a new system that was entirely based on GPU, on CPU, but just one core, that was doing more or less a reliable tracking of the camera, of the depth sensor. And what you see here, I think it's self-explanatory. If you have questions, please ask them and interrupt me at a certain point. I will be eager to answer. Okay, now we have this fantastic thing that is able to track actually the scans or the 3D clouds. Now, why don't we scale it up and go move entirely to 3D? Actually, people have done it. That's one little problem when you move to 3D using only depth data. And you see this problem if you observe a data set acquired in 2D. If you observe, this is a Killian cohort of the MIT. It's a very large publicly available data. Now, if you observe what happens when the robot re-enters in a specific location, this is the path of the robot. Then you see that the person that was driving the robot was doing fancy circles in this location to be sure that presumably was a loop closure, to be sure that the robot had seen enough of the environment so that it was closing the loop. That's also another thing that happens. Normally, when I acquire data, then the map always comes out. When some new student tries to acquire the data, then the map never comes out. Because the slammer knows how the algorithm works, and he knows where it can go and where it cannot go, on the one hand. On the other hand, there is this big issue of the loop closings, right? That actually are the weak point of this graph optimization system, because imagine that if you have a wrong loop closure, a wrong data association, that your entire map will be folded because the minimal energy configuration will be far from the true minimal energy configuration that doesn't have this wrong spring that is folding everything, right? So like, and there was actually like the conjuncture that some people are able to determine to get the SLAM system working. And normally these people by having decent loop closures. And this is done by re-observing repeatedly and obsessively a place in order to be sure that you have seen enough. Meanwhile, well, we couldn't go that far with scans. An attempt of doing reliable loop closings with scans were available, but meanwhile, vision started to take over. And a lot of contribution, a lot of findings and research coming from computer vision started to be used in robotics. And in computer vision, this is what they do. I mean, there's an entire branch of computer vision, those that do structure for motion, that solve this problem since forever. What we needed at this time is to have something which was fast enough to respond certain, to fulfill certain requirements. And so people started looking also in the web mining, and they came out with the idea of using cameras instead of laser first, because cameras were cheap and they provided a lot of information, much more information than lasers. And then the problem of determining loop closures was boiled down to the problem of doing image retrieval. And there were a lot of people on the web that were doing image retrieval. And so what were they using for doing image retrieval? They were using bag-of-word approaches. Where a bag-of-word approach is mostly a system that describes extract features, so interest point with descriptors within an image, and classifies an image. So then classifies an image as a set of words by assigning each of the features to a specific word. And the image then is boiled down to the histogram of the frequencies of the word, that is the features that are appearing in that image. Then two images are similar if they have histogram, which represent the frequency of the appearance of words, between two images is similar. It's like what you do for documents. You count the words, you build a histogram of words, and then you compare how often certain words appear in a document and in another. And if the documents, if these histograms look alike, then you say, oh, these documents might talk about the same topic. This was one way with which, like actually, visual SLAM came into play, and in particular, the saliency of the descriptors. And then also, but there was another thing that computer scientists do since forever, which is when you have to do a search. Normally, you organize your search domain into a tree, and then, and this is what we did. That was the most simple thing one could think of, which is basically organizing the features into a binary tree, or into a, this was a binary tree, but in general into a tree. Now the binary tree can be constructed rather efficiently because you just need to recursively split in two your feature set based on some distance metric, and then to conduct an approximate search, you just have to pick up a feature and to figure out which one is the closest feature in the set. You just follow the tree according to like a search in the tree, each time choosing the left or the right branch based on which of the two subtrees the actual feature is closer. And what you see here is actually our latest algorithm in action. Then I will restart it from the beginning. This is a car moving. This is the path of the camera. This is the tree of features being constructed. This is the query image, and this is the most similar image retrieved. Now the system starts retrieving some image, but they are not that alike because it fails some geometric constraints between them. But at a certain point, and the point will be visible when the trajectory, which is here, starts going back to a known location, so probably soon. Get closer, get closer, get closer. No. It's a pain. They never want to close the loop here. Come on. No. I was here. Okay. All right. Should be. Here. Right. Now you can see that when the robot is closer to a location where it was, a lot of images and consistent are retrieved. So morale of the story is basically, don't throw away some technique just because no one else is using it in this moment, because they might be using it in the past. Now, stop the video. Now, this and other findings resulted in the construction of prominent actual visual SLAM system. The most common one that you might have seen is OrbSLAM. Maybe many of you have heard about OrbSLAM, which is a monocular. In this case, we have a stereo version, but it's a monocular visual SLAM system that has the peculiarity of working really well. And it works because it combines a clever loop detection algorithm with a proper management of the feature. In this case, observe that the map came back again to be done of landmarks, right? Where each 3D point to which we attach the feature, the visual feature acquired at that point, becomes the landmark itself of the map. All right, and that was one track, but still, now we are hot on vision now, and then people are also saying, you know what, features are nice, but you could do better if you regard the entire image as, I hope the video starts. Yes. If you treat the entire image as if it was a surface of intensity values. And in this way, you could define the registration between two images as the transform that minimizes the difference between the pixel of the reference image and the pixel of the reprojected image. So you move the image in order to make the two intensities the same. Of course, you need that one of the two images has also depth values, because otherwise you can't do the projection action. And this was a work of Engels that started a prominent track, and they were able to achieve sub-pixel resolution. Like it's really, really a beautiful work. But still, if this works well for incremental tracking, it doesn't work well for determining loop closures, because once you re-enter in a location, well, this image registration works only if you have a very close estimate of where you were. That is when you run the system at a train rate. But if you enter from another location, well, the two initial guesses might be too different to even attempt a loop closure. So normally they complement the system with some features that they use relying on bag of word to determine the loop closures. Also, our attempt in seeing all this plethora of things was to simplify the existence, because I wanted to have students that were able to work and to put their hands on this pipeline. And so we designed the system, which was ProSLAM, that I will show you now. And it was designed originally by a master student. A visual SLAM system based on features that was originally designed by a master student and then became a PhD student. And it has the peculiarity of being exceptionally fast, just because being done by a student, at the beginning, it didn't implement a lot of little quirks that slow down the computation to favor this 1% or 2% accuracy that often people seek for to publish. But it's tremendously fast, and it was running on a single CPU core. Going on. Oops. And then, again, on the track, this idea of the photometric aspect, so of working on images or on projection of 3D data, could be extended to LiDAR data. Because if you regard the 3D LiDAR points as a depth map, a depth image, then in the end you have two depth images. And on those you can define normals, you can define whatever you want, and you can formulate the registration problem as a registration of two continuous surfaces. And in this way you can achieve improved accuracy over the standard registration algorithm for 3D scans, because you're going at sub-pixel resolution. what you see here is a Kitty sequence which we processed with a system based on, we call it photometric. It's not really photometric, it's dense registration of laser scans. Now, we are at the end of the talk, and I think I have been into the time. Some facts. I left conclusions of 2015 because I originally gave this presentation in 2015. Now I complemented with new material and new things, but I wanted to leave the facts, the consideration of 2015 that were more or less commonly agreed, and then see how many of those hold nowadays. So in 2015, building a SLAM system is really complex. It was also true that marketing papers back then led to the community that the field is closed. Everyone that writes a SLAM paper nowadays says, okay, with this, no more SLAM, right? But back then, and this was even prior on SLAM, very few groups had a real system working in 3D on real large scale back then, right? And at the same time, there is the third aspect, that if you give a SLAM system to someone that is not a SLAMmer, then this system is very likely to fail. Maybe because he forgets to remove the cover from the camera. Now, there was also back then a huge pressure from the industry because they were needing SLAM. They were needing SLAM for Roomba, for the lawnmowers, from a lot of things. And what you have seen in these 5 years is that most of the SLAM research migrated from university to industry. I mean, I made, I think, 7 PhD students between 2015 and now, and they are all working in companies like Oculus, Nutonomy, Toyota. They have been all hired before finishing their PhD, because as long as they were cuffing SLAM, the community, some person with a lot of money were coming. And so, like, basically a lot of engine in the research or workforce that were with effortly trained moved to industry because of obvious money reasons. But they were needing the map, and so now we are in the situation that many companies, they have their decent SLAM systems. Now, what is true in 2020? Well, building SLAM system is really complex. I take it, if you want to build it from scratch, is really, really a pain if you want it to work. But there are effective solutions. I think about OrbSLAM, I think about ProSLAM, I think about 2D laser pipelines. They are available. And if you just like need an off-the-shelf solution that works, most of the cases you have it. And in addition, several companies are also working for us because they are integrating, they are constructing devices. I'm thinking about the Intel RealSense T265 camera that has inside a stereo visual inertial odometry algorithm that tracks the position from like quite accurately. I was impressed by playing with this camera. That provides you a very decent visual odometry that in theory simplifies enormously the construction of a SLAM algorithm, at least for this baseline in several, like in indoor environments, for instance. Here I just cited some pipeline for vision, for SLAM, for laser, but these are not all of them, just like those that we use. At the same time, once you run these open source systems, 100%, or it's very unlikely that you will get it running as accurately as it does on the test data on your own data. The first aspect is that you miscalibrate the system. Maybe you use the wrong camera, or maybe just like you visit a room which is a little bit too dark and then the track breaks. Like, if you want to use this system, very often you need an expert. Not always, but often. And at the same time, if you want to ship it to the industry, in particular, in naive precious SLAM system without any other sensor, well, you have to be ready to failures. And in this case, well, what do engineers do? Well, you have to live with failures and then you have to deal with them. Actually, like this is something interesting to me, actually, to reveal that the system has failed and to undertake proper actions that allow to recover the job done so far. You might say, oh, now I'm lost. I save my map instead of destroying it with wrong closures. I start a new exploration session, and then with time I will try to join the two things if I manage. At the same time, even if SLAM, there are effective solutions for SLAM, SLAM is a melting pot of system and subsystems. There are a million of algorithms that play a game. And actually, like if the algorithms that are used in SLAM are improved, well, the entire system is benefiting. So there is still some research to be done to the component, to the sub-problems of SLAM. I'm talking about graph optimization, I'm talking about image retrieval. There's quite something to be done. Image retrieval in changing seasons. There was a prominent work of Paul Newman that addressed this problem. There are open issues that are there, but I see them more in the modules of SLAM, in the sub-problems of SLAM, than in SLAM. And another interesting thing is that now we have a working machine which has a lot of decent components. Then if so far we were lending parts from computer vision, from many other fields, maybe it's time for us to look in other fields and bring our SLAM expertise to these other fields. And if you really want to have a SLAM system working, and I'm talking to the students, I would start making it the easiest that I can to ensure that it always works. You don't want to have something completely autonomous, but you want to have something that works all the time. And so if in doubt, if you want to work with the human-computer interaction or sort of like that, it would be completely feasible that while I'm steering my robot, it asks me, hey, have I already been here or not? And then just like by telling this one yes, I save myself from acquiring the data another time, because maybe it wasn't done well. So remember then that another aspect, acquiring data is a huge pain. I don't know how many of you were steering robots around. We have several projects, and students hate me for that, because you realize that data are wrong only after you acquire data. And if they are wrong, you have to acquire them again. Another aspect that we have as a group is that as research group is that people leave. And when people leave, also knowledge leave. And if knowledge leave, you have often a bunch of software which is unusable. So we are investing our efforts in cleaning up the pipelines, in doing a lot of software engineering, actually, to reduce the entropy to the maximum in order to limit the effects of the people leaving, because there are people leaving. This month I've lost, in the sense that they have finished 3 PhD students, and so I'm very sad about it. They are excellent, but I'm sad that they, that they leave. Well, this and as a slammer, I have to say that writing slam paper is really, really hard nowadays, because a lot has been done, and you can't invent the so like, if you have an idea, it's very likely that someone else had it before. This concludes my presentation. If you have questions, I'm here available for.
Thank you very much, Giorgio, for your presentation. Was great and amazing, I would say. Um, is there any particular question from the audience or from the participants? I must say that, okay, we just went a little bit out from our schedule.
10 minutes.
Yeah, yeah, we are very, very tight timetable, I must say, but it's fine. because I saw already that many students who were attending your seminar just left.
I'm sorry.